So thank you very much. So after such a wonderful music, I have nothing to say because they already illustrated very well how I feel the universe is, much better than what I will do. So you heard this morning many intriguing properties of neutrinos. They had a fundamental role in the evolution of the universe, in the Big Bang, in the reason perhaps why antimatter disappeared from our universe, and in the evolution and the death of stars. What we know is that these particles, they interact very weakly with matter. Matter is practically transparent to them. And you need an amount of matter which is comparable to many light years of lead in order to stop neutrinos. We know that there are three flavors of neutrinos: the electronic neutrinos, the muonic neutrino, and the tau neutrino. And another unique property of this particle is that they can change flavor during their path. So they can transform from one neutrino species to the other one. And this is the phenomenon that we study, which is called neutrino oscillations. And another striking property is that they are the lightest particle in known particle in nature. And this is something that we really do not understand, but which is intimately related to some fundamental physics that we have not discovered yet at the level of grand unification theories of a unique description of nature. So all this is really nice, but it came, most of that came totally unexpected from a collection of experimental facts. All these properties that I showed of neutrinos were not expected from theory. It was the other way around. And even the concept of the neutrino itself was born in 1930 as a desperate remedy in order to save the law of energy conservation by this physicist Wolfgang Pauli. So we come back to what is inspiring our work since about the year 1600, when Galileo Galilei invented the experimental method, and this was the birth of physics and modern science. So the experimental method tells you two very simple things: that the description of nature is quantitative, and that we have not to impose our vision to nature, but to ask nature itself how it works by performing experiments and measurements. So experiments and measurements, they have really a key role in the understanding of nature, but sometimes they can bring puzzling and uncomfortable results, like the one that I'm going to show you. So I'm trying to explain you how we perform this measurement of the neutrino velocity. So we have the source of neutrinos is in Switzerland, in Geneva at CERN, and then the neutrinos travel in the Earth crust, which is transparent to them, over 730 kilometers, down to a location which is nearby Rome. It's at about 100 kilometers from Rome, where there is a mountain, the Gran Sasso, in Italian means big stone. And under these mountains, we have an underground laboratory, which is shielded by 1,400 meters of rock, which eliminate the cosmic radiations, particles which are coming from space. They are suppressed by a factor 1 million with respect to what you would get outside this laboratory. And the laboratory was built in the 80s, already with the experimental holes oriented in the direction of CERN. This was a very good vision in view of this kind of experiments. So the measurement itself is very simple. You have to measure the production time of neutrinos at CERN, and then you have to measure the time they interact in the detector which is under this mountain. And you have to measure the time in a coherent way. The definition of time should be the same for these two measurements. And then you have to know very accurately the distance which has been traveled by these particles. The other feature of our work is that we performed all this analysis in a blind way, because as experimentalists, we do not want to bias the result of the measurement with our beliefs. In particular, I must say that I didn't believe at all that neutrinos could be faster than light. So we protect the data. We artificially put a bias in the data that we can remove at the very last moment, which prevents us to know the result until we have completed all the work, and in particular, the assessment of all the experimental uncertainties which are related to the measurement. So, by the way, we do not have any tunnel going from Geneva to Gran Sasso, as somebody understood. So now I will explain you how we produce neutrinos at CERN. So we have an accelerator which every 6 seconds accelerates something like 40,000 billions of protons at a very high energy of 400 GeV. So 400 GeV means that these protons reach an energy which is about 400 times their mass, which is very large. And this beam is extracted from the accelerator and sent on a target of graphite, which has to absorb enormous shocks from all this energy which is coming from the accelerator, which on average is equivalent to 500 kilowatts. So then in this target, protons interact with the nuclei of the atoms of graphite and produce secondary particles, which are collected with a series of magnetic lenses in a parallel beam. So these particles are pions and kaons. They are particles lighter than the proton, but if you want, of the same family of protons, a family of particles which feel strong interactions. And then these particles, they are sent in a vacuum pipe, which has a diameter of 3 meters, and it's 1 kilometer long. And in this pipe, they can decay in whatever point of this pipe in muons and muonic neutrinos. Muonic neutrinos will just continue the travel on the direction of the initial direction of this particle. They will just continue the travel to Gran Sasso. So all the game is to have oriented correctly all this structure in the direction of the laboratory, which is in Italy. So this is not a continuous beam. It's a beam, it's a pulsed beam, which has these flashes of neutrinos every 6 seconds. And in particular, there are 2 flashes which are separated by 50 milliseconds, and each flash lasts about 10 microseconds. And this gives us already a good timing, because we know when these neutrinos are produced. They're not produced continuously. So how do we know then the time, the starting time? Because we cannot measure these neutrinos. We can only measure their parents, the protons, and that we can measure with a very good accuracy. So then in order to know the complete time which is taken by these particles to reach Gran Sasso, we assume that everything from the time we measure the protons down to Gran Sasso moves with the speed of light, which is a very good accuracy, which is a very good assumption with high accuracy. It's just if the reality introduces just a little delay, which goes in the opposite sense of what we measured. So here I can show you how we measure the protons. So in this slide, you can see the accelerator ring, which has a diameter of 2 kilometers. So you can see here that it crosses the border between Switzerland and France. And then in this point where the proton beam is ejected, we can measure the current of these protons. So you know that electrical current is made by a flow of charged particles, the electrons. With the protons, we can do the same. We can measure the current of this pulse of protons. It's something like this recorded waveform. So this is what you would see at an oscilloscope. And we measure that with this instrument, which is on the accelerator. And all these waveforms we store because we can use them in order to compare their timing with what we observe in Gran Sasso. So you see that this electrical pulse lasts about 10 microseconds. So in Gran Sasso, then we see the neutrinos. When we see the neutrinos, it's a kind of visual effect, which is shown here. We detect neutrinos with a detector which gets little flashes of light, and then they can be represented in this kind of plots, where you can see here that at a certain point inside the detector, there is some activity. You cannot see the neutrino arriving. You can only see the secondary particles which are created by the neutrino interaction. And in particular, you see this long track which is about 20 meters long, which is crossing the entire detector. That is the muon. So in this kind of interaction, the neutrino has transformed it in its charged brother, the muon, and it has exchanged some energy with the quark, which has recoiled and has produced this little blob, which you see in the detector. In another kind of interactions, which are called neutral currents, the neutrino stays neutrino, and you see only the recoil of the quarks. So you see only a little blob. And then there are a third category of events where the neutrino interacts in the rock, and we just get the muon penetrating inside the detector. So this is the way we see neutrino, and we can measure accurately the time of production of all these little flashes of light in our detector. Then if we look at the time distribution of whatever we observe in the detector continuously, we can see the time structure of the beam. So we can see that there are a few events which are a little bit everywhere in time. These are the residual cosmic particles which are arriving from space. And then if we relate the time origin of what we observe in the detector with respect to what is produced at CERN, we can clearly see two spikes which are separated by 50 milliseconds. These are the neutrinos. And if we zoom, we can see a distribution which is very similar to what I showed you before at CERN concerning the protons. So the neutrinos have a similar time distribution as the protons. So here I show you the principle of our measurement. So we want to measure the time of flight of neutrinos. So at CERN we can measure the time distribution of protons. Then we can know accurately the distance between the point where we measure the proton and our detector. We can shift in time by correcting by the propagation delay the distribution of protons, and then we can compare to the distribution of the neutrino events on the other side. So this is a quite, at the end, simple procedure where you don't know really for each neutrino when it was produced and when it was detected, but statistically you can know for all the neutrinos how do they compare with the protons which have generated them. It's like looking at a big race of many people moving at the same time and then computing on average their speed. So in order to do that, you need to synchronize the time in the two places. And this is done thanks to the GPS signal, which gives you a common origin of time. And then by using all these tools, you can check whether these two distributions, they exactly overlap, and this should happen if neutrinos move at the speed of light, or if there is a little discrepancy, which is what we call here delta t, which is the difference between the time of flight that you would expect from neutrinos if they travel with the speed of light in vacuum, and the time of flight, the real time of flight they have in nature that you extract by comparing these two distributions. So a few words about the GPS. The GPS is really a wonderful system, and this was one of the things which was more exciting to use in the years we have been performing this measurement. So most of you use the GPS in your car or now even on the portable phones. You have understood that the GPS localizes you in space. But in reality, the GPS localizes you in a four-dimensional space, the space-time. So it finds your position at the same time in space and in time. And this is why we can use it for this particular measurement. So this is done by observing at least 4 satellites, the transmission delay of radio waves, which are emitted by 4 satellites. And if you measure that by solving a system of 4 equations in 4 unknowns, you can find the position and the time of the observer. If you know already your position because you don't move, this is the case of the laboratory in Gran Sasso, apart a little exception that I will show you in a minute. 1 satellite will be enough in order to measure the time. So this you can do even in a better way, which is called the common view mode, where you make sure that from the 2 sides of the Earth, you're looking exactly at the same satellite. Then if you use a special GPS receiver, And this technique and an atomic clock, which must be coupled to the GPS receiver in order to guarantee that your time is stable in between different GPS observations, you can perform a time transfer between these two sides of the Earth, which are 730 kilometer distance, with the accuracy of 1 nanosecond, which is quite a good accuracy in time. And this is what is also used in the definition of the International Atomic Time. It's a procedure which is used in order to synchronize atomic clocks, which are in different places of the Earth. So here you can see quickly the two systems which are installed here at CERN and here in Gran Sasso with the GPS receiver and an atomic clock. And the other ingredient is the distance. So how do we know the distance from these two places? This is still done with the GPS. But there is a complication because our detector is underground, where we cannot receive the radio waves from the GPS satellites. So these measurements must be done outside this highway tunnel, which brings to the underground lab, which is about 10 kilometers long. And then with a set of triangulations, we can bring this information underground. And in order to do that, we had to stop the traffic, partially the traffic in the highway for 1 week. And we could do that with the 20 centimeter accuracy. By stopping completely the traffic, we could have done that with the 1 centimeter accuracy. But 20 centimeter accuracy was already enough. So our system is very sensitive to tiny deviations. Like here, you can see the evolution of the position of the antenna of the GPS as a function of time. So you see these tiny movements of a few millimeters per year. These are related to the continental drift. And the jump of about 7 centimeters, which is related to the earthquake, which happened in 2009 in L'Aquila. So we did this game for about 15,000 neutrinos. And this here you can see how they compare with what you expect from the protons. So the neutrinos are these dots, and the protons is the continuous red line. And this is the result of the blind analysis, which shows you an anticipation of neutrinos of about 1 microsecond, which doesn't make sense, but this was done on purpose in order not to know the real anticipation. And it allows us to perform a series of cross-checks to check the stability of this result as a function of time during many years, if it was the same during day and night, during the warm season and the cold season, and so on and so forth. So here you can see a timeline of the measurement, how it was performed. So we observed the first neutrinos in 2006. And then we studied how to improve our system for 2 years in order to perform this measurement. And finally, we took data in a completely blind way for about 2 years. And at the same time, we performed all this calibration, which allowed us to know the time at 1 nanosecond level and the distance at 20 centimeter with 20 centimeter accuracy. In March last year, we opened this blind box, and we were extremely surprised to see that neutrinos were arriving 60 nanoseconds earlier than light. So you can imagine it as a rush over these 730 kilometers between the photons and neutrinos, and the neutrinos arrive with 20 meters earlier than the photons. So it's a very tiny effect. And then we spent 6 months in cross-checking all that, and in September, we announced that to the rest of the physics community. And in November, we performed another measurement that I will shortly explain to you here. So the standard measurement is done with a long pulse of 10 microseconds, and we don't know individually for each neutrino the time. But in November, we studied a way where we could measure for each neutrino its time of flight. And this is done by using a beam of very short pulses, which are isolated in time. They are separated by about half a microsecond. So we measure 20 neutrinos like that. And they had the same accuracy of 15,000. This system is much more accurate, and we found the same result. So just to conclude here, there is a slide that we showed at CERN at the seminar on September 23rd, where we say that we spent many months in trying to explain this observed the effect in terms of known physics and uncertainties of the measurement, but we didn't succeed. So we interpreted it as a deviation with respect to the speed of light, which is a tiny effect of 10 to the minus 5. although with a very good accuracy, 6 times the error of the measurement. And we also said that we, despite the very good accuracy of the measurement, we were going to continue our research on this field, and we wanted to abstain from any interpretation of this result. So, conclusions. We worked on the basis of this sentence of Galileo, measure what is measurable and make measurable what is not yet measurable. So we developed a new technique in order to measure the speed of neutrinos with about 10 times better accuracy than in the past. And this was based on an unprecedented mixture of high accuracy metrology and techniques of particle physics. We obtained these very puzzling results, so we decided to communicate it to the rest of the physics community in order to get help in its investigation and interpretation. And for all results in science, we will continue on our side to do to perform some measurements, but the key point is that any physical effects must be independently reproducible. So the key point in the next months, years, will be the refusal or confirmation of this effect by independent measurements and experiments. We had already some good effects of this result, which was the diffusion of these new measurement techniques, a lot of new theoretical ideas, even if we abstained from that. There were about 200 papers written on this result. And as a distinguished theorist said, the nice aspect of this result is that it forced us to think in new ways about things that we thought we already understood, and a great interest in the public for physics, science, and its methods, which I think is the reason why I'm here also today. So thank you very much.